So where we ended was our quaternary amines. We said the one synthesis option that we could go through and do if we backtrack to force one product. If we add an excess of the alkyl halide, we can take it to the quaternary amine. That is really the only synthetically useful substitution right now with our amines. Because as soon as we do one substitution, the amine becomes more active to substitution, and that becomes problematic. Okay? So when we talk about substitution with amines, the only thing we got is to make it a quaternary amine. Okay? So why do we want a quaternary amine? Oh, seriously? So why do we want a quaternary amine? Well, what happens if we had an oxygen where we protonate it to make it positive? What happened to the oxygen? What's that? Didn't like the charge very much, so what did it do? For those of you guys trying to figure it out, it did not pick up hydrogen because it would have to have electrons to pick up hydrogen. We have a positive oxygen. There's no way it can pick up hydrogen. What happens? It could kick off a hydrogen. It could become acidic. That is a valid possibility. What else could it do? It could leave. Could act as a leaving group, thus making our carbon electrophilic. Right? Which would facilitate either substitution or, what was that, Tyler? Elimination. So with that reagent, we could either do a substitution reaction or an elimination reaction. Remember, the nitrogen's not very good at substitution. Our only option for our nitrogen substitution is to turn it into the quaternary amine, and that's the end of it. Okay? Which means the path that we're going to go with our nitrogen, elimination. To do an elimination, what do we need? Need a leaving group. So if we add CH3Br in excess, we would have that leaving group because we'd have that quaternary amine. What else do we need to help facilitate an elimination? A strong base. Right? Strong base, typically if we were thinking E2, if we were thinking E1, we would typically see not a nucleophile, that's substitution. Heat. Right? So in this case, if we go through, instead of just adding CH3Br in excess to do our full substitution, we also add NaOH and sodium hydroxide. Well, NaOH is a really good base, and delta is a really good symbol for heat. That would do an elimination. Right? So we could eliminate the nitrogen from the structure. If we do an elimination, what would we end with?
A double bond.
End with a pi bond. Okay? Depending on where our leaving group is, we could get varying options. So we could get the red one, or we could get the blue one. And actually scratch that. Let's try that again. We could get the red one, or we could get the blue one. What is the difference between those products? So we could go with stability. If we're going to reference stability, there's a term that we could use, particularly if we're looking at energy of our products. We could call it thermodynamic. Which of these would be our thermodynamic product? The red one. And the blue one would be kinetic. When going through and doing elimination reactions, it was observed that we almost exclusively get the thermodynamic product. Okay? Who observed that? Chem 1 knowledge. Old white dude, fair enough. Old right Russian dude. Try again. Zaitsev. Okay. What that is ultimately saying is that if we look at an elimination reaction, reactant to product, our products are higher in energy. Because we're going higher in energy, the product that we're going to form needs to be the lowest energy product. Why would it need to be the lowest energy? Well, if this one's the kinetic product, and this one's the thermodynamic. According to another rule, Hammond postulate, the transition state is closest in energy to reactant or product that it is closer to. It's closer in energy to the product, so our transition state energy drops. What does that mean? Our thermodynamic should theoretically go a little bit faster. Okay? That was the overwhelming observation made by Zaitsev. And so we said we always want to form the thermodynamic product, the most substituted. Okay? He didn't have energy diagrams to deal with it. We do, so we've got a little bit more information. Okay? How much that transition state shifts depends a lot on steric considerations within our kinetic and thermodynamic. The kinetic should go faster because it is more accessible on the outside, okay, than our thermodynamic because our hydrogens are more buried on the inside. Because there isn't a whole lot of steric consideration here, that difference is so minuscule the thermodynamic trumps. But what happens if sterics becomes a really big issue? If sterics become a big issue, that thermodynamic product then does what? Or transition state? Goes up in energy. If that thermodynamic transition state actually goes up in energy, what ends up happening? We end up not forming the more substituted pi bond. Okay? That's a steric consideration happening in that transition. It's a very small, nuanced system, and it happens in very rare cases. Okay? So rare that when it was discovered, what did we do? We named the reaction after the person that discovered it. Okay? That's how rare it is. That elimination is known as a Hofmann elimination. And we end up forming the kinetic product, the least substituted pi bond. Okay? If we draw out the product of just that first part with our excess bromide, or CH3Br, we end up with that quaternary amine. Does that look kind of big? Is sterics going to play a role? Yeah. This is the classic Hofmann elimination. Right? So when you talk about Hofmann eliminations or heard about it in first semester, you probably weren't referencing the amine functional group because the amine functional group is a challenging one to deal with. That's why we talk about it in second semester. And instead, we reference using bulky bases. Why would a bulky base favor a Hofmann elimination? Sterics, it's bulky. That's exactly why it goes to the kinetic product. The exact same thing can happen with our substrate. And that is what happens with this reaction. We run the elimination and we end up with the Hofmann product. It is strictly a steric, well, close enough to strictly a steric argument. Okay? Sometimes sterics make a larger issue than others. Okay? Ultimately, you need to know that it does that. Why does it do that? Okay, does anybody remember the word Newman, or the name Newman? Okay, for those of you being like, nah, I don't really remember that. You should actually, it's a microphone company? Oh. Learn something new every day. You would have to look at a Newman projection to see why the one elimination is favored over the other. Cardi did a phenomenal job drawing out the Newman projections for this, so I'm not going to bother to do it. If we look at the Newman eliminations, okay, we end up seeing that there's only one configuration that actually allows for the elimination to occur. Because we're using a strong base, it has to be E2. The complication with E2 is anti-coplanar, okay, or periplanar. Periplanar is not the right word. Anti-coplanar of our leaving group and the hydrogen removed. We see that in this Newman projection. If we try to do that in the other carbon, to get that elimination, we get a steric blocking. That sterics prevents the hydrogen from ever achieving that anti-configuration. If the hydrogen can't achieve that anti-configuration, what happens? It doesn't react. Nothing happens. And we don't get the elimination. So the only way it happens is if we achieve that orientation. That happens only if we do the Hofmann elimination. We form the least substituted pi bond. Right? It's a really neat phenomenon. I would love to draw it out and talk about it more, but we're just going to move on. CH, do you see any reactivity of a CH bond? Silence is also good for that because no, we don't see a lot of reactivity for a CH. Why do we not see reactivity for a CH? Silence is not good for that answer.
Because the electronegativity difference is not that high.
There's no difference in electronegativity to cause a polarity of that structure. So to get your alkanes to react, we would have to do something kind of radical. Okay? We'd have to do a radical reaction to get an alkane to react. Okay? But what we can do is bring it near another functional group and see if that other functional group can cause the alkane to be reactive. Okay? This does sound a little bit weird, but if we look at the OH from an alcohol, that pKa is roughly what? 16. If I bring the OH of an alcohol near a carbonyl, the pKa of that OH becomes 4. It's only 12 different. That's 10 to the 12th difference. That's a huge difference in reactivity. So huge that we actually call it a new functional group. We have an alcohol in one case, and in the blue case we have a carboxylic acid. We're doing the exact same thing with our alkanes. We want to bring them near another functional group. Okay? In this case, I took that center carbon and replaced those hydrogens with a carbonyl. So pretty much the same thing we did with the alcohol. Does that change the reactivity of the alkanes? Yes. Okay? So let's draw in all the hydrogens. Should we have to draw in all of those hydrogens? Some of you are saying no. Are you getting all the questions right when they involve this kind of chemistry? If your answer is yes to that, then you don't have to draw in all the hydrogens. If your answer is no, I'm getting a lot of questions wrong, then you need to draw in all the hydrogens. Okay? That's why we put the hydrogens in. If you understand it, you don't have to do it. If you don't, then you have to show them. Okay? Why should we not have to show them? Well, these 3 hydrogens versus these 3 hydrogens, are they the same or different?
Same.
They're the same, which means I can ignore. Okay? How about the 3 hydrogens that are labeled right now?
Same.
They're the same, really? Isn't this now blue hydrogen different because it's further away from that carbonyl? None of them are further away for several reasons. Okay? One reason, I heard a good one, this is a sigma bond which can freely rotate. Another reason, that is a tetrahedral carbon.
Yeah.
The bond angle is 109 for all of them.
120.
Okay? 109 for tetrahedral. 120 is trigonal planar. Okay? All of them are perfectly identical. Okay? Because they are all identical, I don't have to show all of them, and I can get away with just showing one. Which one do I pick? I usually pick the one furthest away from everything else. Why?
Looks better.
It's easier. It looks better. Okay? Is that hydrogen now reactive? Okay? So how might it react? Okay? As a hint, I'll give you 2 options.
It might leave.
Okay? It might leave. If it leaves, it takes those electrons with it, right? So we'd get H with those 2 electrons. Okay? And you might be like, well, isn't H with 2 electrons charged?
No. Not yet. It's H minus.
Yeah, it is. It's H minus. Okay? That should be reflexive. It was phrased in a way to trick you. I apologize. Okay? And so most people will catch that's H minus, and they go, okay, well, now what? It's not a huge issue. There's another flippin' issue.
It's not stable.
What's not stable?
It's hydride.
Hydride. Okay, there's another big issue.
The carbon.
What about that carbon?
Is it positive?
It's positive. Really? It doesn't look like it's a problem right now. Why is it positive? Okay. So if I understand my curved arrows, this arrow means electrons left with the hydrogen. So I could say that carbon lost electrons. It must be positive. Right? If I don't understand curved arrows, is there another way to do it? Yes, we could calculate formal charge. To calculate formal charge, how many valence electrons does carbon have? 4. We should be a little faster than that, believe it or not. How many bonds?
4. 3.
If it's 4, what's its formal charge? 0. Damn it. So it must be 3. You're just throwing crap at the wall and hoping it sticks. You need a better explanation than that. Okay? How many bonds does it have? 3. I only see 1. Remember how we said if you're getting the answer right, you don't need to specify it? If you're getting the answer wrong, you need to specify it? Backtrack. Did you do anything to those 2 hydrogens? No, which means they're still there. Okay? Which means 3 bonds. The formal charge would need to be positive. Okay? If I was trying to figure out the formal charge because I didn't know it, how do I know? There's no positive there. How would I know there's only 2 hydrogens? I would have to have remembered what happened back here. If you're getting answers wrong, it's because those implied hydrogens you're forgetting about and you're not transferring them, which then goofs your charges. Make sense? So be careful with implied hydrogens. Okay? So we heard a couple arguments about stability and I went off on a rant. Let's double back. H minus, is that stable? Why not? Charge. Negative charge. So charge is immediately a bad thing. What about size? Is it big enough to stabilize that? No. Hydrogen is literally the smallest atom we've got. So no. Is it electronegative? No. Is there resonance? There's no molecule. No. Nothing about that is stable. What about the positive charge? Not stable because?
Carbon doesn't like that.
Carbon doesn't like positive charge. So I couldn't say draw something like this. That carbon's not allowed to form? Carbocation? Oh no, it is. Well, why is that one unstable?
It can be stabilized.
It can be stabilized. How can it be stabilized?
Resonance.
Resonance. Okay, so I would take the electrons up there and I would do that to stabilize it. What are you shaking your head at, Lee? You're like, no, don't do that. Why is that an awful arrow?
Because your oxygen would be
Electrons are going
charged.
up.
That is a bond shared between carbon and oxygen. You just took the electrons and you said that they would leave oxygen. Oxygen is the second most electronegative element. Do not let any atom take electrons away from it unless it is oxygen or fluorine. Why are those 2 exceptions? Same electronegativity or greater than. Okay? That's why we manipulate these things. That's why they work. This is why electronegativity plays a big role in how these things work. So do we have a resonance option? No. Okay? Is there a substitution effect? Because if I drew out, say, this one, isn't that, whoops, sorry, let's try that again. I wanted this one. Could I form that one? Yeah, I can form that one. Why is that one okay, but the blue one / green not? Substitution. Okay, a tertiary effect versus primary. Okay, so in our blue path, everything about that path screamed unstable and wrong. Does that mean you should not take notes on it? Okay, let's point it out. Based on the pencil movement, you all agree with that we should not take notes on that. That is a wrong path. We should never take notes on wrong paths. What's going to happen when you take the exam? You're going to go down the wrong path. If you don't know why it's a wrong path, you think it's right and you get the answer wrong. You have to be able to know why a step is wrong. That's why we talk about wrong things. Okay? This is huge in second semester. First semester, guess how many paths there were? 1. You will be lucky to have a question with 2 paths. Okay? Most are 3 or 4 different things that you could possibly do. You have to be able to evaluate why 3 out of those 4 are the wrong thing to do. And you have to be able to do it in under a minute and a half. minute and a half, where's this weird number? 70 questions, hour and 10 minutes, final exam. Okay? That takes practice. Okay? What's that practice? Drawing the wrong path and being like, well, that was a wrong thing to do. Make sense? So what's the right thing to do? Eject hydrogen without the electrons. I don't like that terminology.
Need a base.
Okay? Instead of hydrogen taking the electrons, carbon takes them. I like where you're going, Milana. Slightly too far, but ultimately the right idea. Okay? Let's keep it simple. Okay? Before we even get into this, there's two paths. Did we have a way to be like, this path was probably a bad idea? You're like, no. What's the electronegativity for carbon? 2.4, 2.5. What is it for hydrogen? 2.1. Which one's more electronegative? Where should the electrons go? Okay? Having that electronegativity back there can help you. The difference there is tiny, which means a subtle change to the structure can overwhelm that electronegativity difference. Okay? Particularly if you move into biochemistry. Biochemistry just does whatever the hell it wants. So we take those electrons and we put them on the carbon. Okay? And H plus. Now that it's hydrogen, we're okay putting H plus. We remember the plus because it's hydrogen. As soon as it's any other atom that's supposed to carry the positive, we almost always forget to do it. That's why you should draw out your structures. What happened to the carbon?
It's minus charge.
It's minus charge. It just gained electrons. Should a negative carbon work? Well, charge says it's bad. Size, carbon's pretty small. That's bad. Electronegativity, that's bad. So we got 3 strikes. Good thing we get 5 tries. What's the 4th try? Both of these structures represent the same compound. If I want to evaluate stability, which of those 2 structures should I look at? Red or green?
Green.
Why green?
Where more electronegative atom is charged.
The more electronegative atom is charged. What does that mean?
It can hold it.
Oxygen can stabilize the negative charge. Fantastic. So that is a phenomenal way to think about this. If I want to think about how it reacts, which structure should I be looking at? I should be looking at the first unstable one in this case, which means I have a negative carbon. What could a negative carbon do?
Act as a nucleophile.
It could share with an electrophilic carbon in a substitution reaction. So it's acting as a nucleophile. Or
It can absorb an H plus.
it could absorb an H+. It could act as a base. Make sense? So I need to be thinking of those pieces as far as their reactivity goes. Right? The extra kind of fun piece beyond this is that if we kind of equate this out, like stabilize it, we want something to temporarily stabilize that negative oxygen. What's our positive atom that could stabilize a negative oxygen? Hydrogen. What functional group do I have? I have the enol. That enol chemistry shows up again and again and again. If you have to take biochemistry, that's what drives biochemistry, is the enol chemistry. Okay? So it is incredibly important to acknowledge where it's coming from. Where did it come from? I removed a hydrogen from an alkane. Well, that shouldn't happen. As soon as it's next to a carbonyl, it can. Make sense? Okay. So what could we do with this? Okay, well, how could we get it? We've seen it before. If we took a triple bond and I added sulfuric acid presence of mercury and water, what happens? As a hint, this sequence of reagents adds H and OH across a nonpolar pi bond. Do we have a nonpolar pi bond?
Yes.
Yes. We had H and we had OH. Yeah? Do we have a nonpolar pi bond? Still? Yeah, so it could theoretically react again. Whoops, as I draw the pi bond again. It will react where it places that second OH at that exact same spot. Right? That chemistry for that red one, we don't know yet. We haven't talked about that. I think that's the end of this unit. That's known as an it's acetal-like. It's technically a hydrate. Okay, why would we call it a hydrate?
Because it has water.
To go from the blue structure to the red structure, what did you do?
Add water.
You added water. What functional group is the blue structure? Isn't it alkene?
No, it's an enol.
It's an enol. What do enols do?
Tautomerize.
Tautomerize to
In this case, a ketone.
the ketone. What happens if I react water with a ketone? It would become hydrated, right? I would add hydrogen and OH. What does it look like? It looks like the hydrate. Okay? So really any way you swing at that one, you end up at the same spot. Some of that chemistry isn't as obvious as others. For going red to black, we haven't officially approached that topic yet. Going blue to black, that gets addressed in first semester, and it's been addressed now multiple times this semester. Okay? Whichever path works for you is what you should be using. Okay? So we can get our enol and our enolate. It can happen in the presence of a base. Okay? That tends to be the easy one to see. Why is that an easy one to see? What do bases do? Take away a hydrogen. So we remove an acidic hydrogen. Oh, ta-da! Now there's my enolate. That makes sense, right? How do I do it with an acid? Can't take away a hydrogen. I'm adding hydrogen. Where did you add the hydrogen?
On the oxygen.
We added it to the oxygen. What is the result of that? A positive charge on an oxygen. Does oxygen want to be positively charged? No. So what does it do?
Steals electrons.
Steals electrons from the carbon. What are we drawing? Resonance. Good answer. I would end up with a positive charge on the carbon. That's actually a really bad Lewis structure. Why?
Because you don't have your octet.
Missing octets. That's still not the enol. What has to happen?
The carbon has to steal electrons from the CH bond and turn into a pi bond.
Why would that hydrogen be acidic?
The oxygen.
Because it's near an electron.
Partly because of the oxygen. Also,
There's a positive charge. It's
octet. We've satisfied octet. By removing that hydrogen, all of our atoms now have the octet. So we can get to that enol structure either through an acid catalyzed reaction or a base catalyzed reaction. Okay? The base one, in my opinion, tends to be a bit more explicit, a little bit obvious, more obvious to see. Okay? It doesn't guarantee it, but it's at least in my mind a little bit easier transition. Okay? In both cases, this process, either going from the keto form to the enolate or the keto form to the enol, is known as a tautomerization. Okay. Why is it important? Take biochemistry. Okay. Literally everything in biochemistry comes from carbohydrates or comes from enolates. Okay. The thing that's really powerful about this, and again, it's easier to see with the enolate, is if that oxygen shares its electrons down, I generate a nucleophilic carbon. Why is that a big deal? Can carbon stabilize a negative charge? No. What did I just make?
A stable negative.
A negatively charged carbon. That's phenomenal. I can now react carbons with other carbon structures and make larger things. Right? Up to this point, all we could do is really change functional groups on and off. Okay? That would be like saying, I can build a house, but the only thing I can do is change the doors. I can make the windows different, but the size of the house never changes. As soon as we have negative carbons, I can now take that house and turn it into a mansion. I can take that house and add floors on it and turn it into a business office. Okay? I now have the functionality to be able to do a lot more things. Okay? So, we need to find electrophiles to react it with. Okay? Hydrogen's kind of a borderline one, okay, but we'll keep seeing it referenced as kind of an electrophile. It's borderline because
It has a positive charge on the electron.
but isn't that what an electrophile is? It's supposed to accept electrons, so shouldn't it be positive? Why is hydrogen a borderline electrophile?
Because it can go the other way.
Not that strong.
Say that again.
It's also an acid.
It's an acid. I would classify hydrogen not as an electrophile, but it's better defined as an acid. Okay? Chemistry is identical as far as electron transfers go. It's better referenced in acid-base chemistry than in electrophile chemistry. Okay? Halogens. Okay? Elemental halogens are phenomenal electrophiles. We'll keep seeing them pop up. We already saw them show up with our alkenes. We'll see them with our enols too. Carbon structures. Right? Carbon's a great electrophile because I can attach a halogen, electron withdrawing. I could attach OH. Not as good. Why not?
Because it's not as electron withdrawing.
OH, I would argue, is actually more electron withdrawing than the bromine. Not a good leaving group. Right? We could switch it to the nitrogen. That could potentially work. We could switch to... Where's the electrophile in the carbonyl? Not so much the pi bond, but the pi bond is where our reactivity is. So zeroing in on the pi bond I love, but saying that the pi bond is an electrophile is questionable because the pi bond is a source of electrons. But if I go through and say, well, I know pi bonds are allowed to move via resonance,
You have an electrophile.
I could draw out the... It helps if you draw the same structure, Mike. Let's try that again. What can I identify at that carbon? That carbon is our electrophile. Okay? So thinking about those bond polarities allows us to see that. Okay? Nitrogen as a positive charge, acting as an electrophile, very, very rare. But it's right, it's positive up here. Yeah. Is it acting as an electrophile?
No.
No. It's acting as a leaving group. It's taking electrons that are already around it. It can't accept more electrons. Right? So when do we see nitrogen electrophiles? Get it?
I laughed.
It's okay. You don't have to. They're blue. Is that better? No. Whatever. Oxygen is also exceptionally rare, so it's limited in reactions. I expected Lily to not respond because that's a whole other genre of stuff for you. It's okay. So limited in reactions. We're looking at epoxides. Or not epoxides, peroxides. Blue, have you ever heard of how to order a steak?
It's
Rare, medium rare, all that. One of the ways to order a steak is
blue.
blue.
That's messed up.
It's lower than rare. Right? They're so rare, they're blue.
Steak tartare.
Which is really good, yeah. Okay, in any case, oxygen-oxygen bonds, the peroxy. Okay? Also very, very rare. That's pretty much the only place we see it. So pretty much for the rest of the semester, what we're going to do is be like, here's a nucleophile. And then what are we going to do?
Find the electrophile.
React it with this, react it with this, react it with this, react it with this, react it with that, react it with that. For the rest of the semester. Here's a new nucleophile. Do all those reactions again. Okay? What makes it frustrating at some point for me is that we're repeating all of that chemistry, and yet when we go through and do it, We go through and say, well, this one is now called Grignard. You mean all I'm doing is reacting the same way we've talked about reacting things. Why did somebody get to attach their name to it? Good point. Somebody did enough science. Let's be nice. Somebody did enough science to attach their name to it. Okay, so we will encounter a bunch of named reactions. So ultimately, just how do we match these things up? Okay? So, our easy reactions. From the enolate structure, it can act as enolate. What can the enolate act as? A nucleophile or base. Okay? This means that to do a substitution reaction, what do I need? I need an electrophile. Okay? Notice we keep referencing these terms and trying to align them. Kind of like how we've referenced the 5 rules of stability thing. Okay? Which showed up a bunch on the exams. And how substitution, addition, elimination, radical, and acid base also showed up on the exams. Okay? You need to know those basics. Because that's the overarching thing that allows us to organize this. Okay? So once I generate it, what can I do? Well, I can throw in an electrophile. Okay? What kind of mechanism do you think is going to run?
SN2.
Why SN2?
You've got a strong nucleophile.
Negatively charged, so we're looking at a strong nucleophile.
Good leaving group.
Okay. We have a good leaving group. Which mechanism prefers a good leaving group?
SN2. 2 type, actually.
All of them. All of them prefer a good leaving group. So I don't like referencing the leaving group. Look at the substrate. The substrate's a primary leaving group. Okay? That primary favors SN2. So we'd be expecting a backside attack in this reaction, go through and get our products. We'd have to be concerned about stereochemistry because we're getting inversion, right? So should I be concerned about drawing wedges and dashes?
No.
Why not?
Because you don't have a stereo center there.
I don't have a stereo center. Okay? That sucked in our first unit. We had to worry about stereochemistry. In OChem 1, we had to worry about stereochemistry. Most of OChem 2, guess what we do with stereochemistry? We don't have to worry about it. Okay? That doesn't mean it's not there. That just means we typically get 2 products and we just don't care to point those out. Okay? In this case, the 2 different products that we get, or the one product, it doesn't matter, sorry, ignore me. Okay? We could have done it with Br2. What do we get? Remember, bromine's a good electrophile because one bromine wants to leave, making the other one positively charged. The result, we get the bromine connected. Okay? Make sense? We've got a couple head shakes, yes. Okay. Kind of lied. Okay, because in that previous slide we said we just really focus on the base ones. We can also do it in the presence of acid. I also lied because for that reaction, I said the product was this, right? Yeah? Didn't I? Yeah. But I didn't really lie because you all reviewed your notes from Monday, and you can tell me that I actually told you what that answer should be. How many people reviewed your notes? Okay, what's that? Do you see the word excess? No. So I know where you're going, but not quite. You're saying it keeps reacting. Why does it keep reacting? Because she's right. This is the product we get.
Bromine is electronegative enough that it made the other hydrogens more acidic than the first one.
Okay. If we go through and run the reaction, the product that we expected was just a single bromine, and we got one with more bromines. Why? Notice I drew the starting material. Why did I draw the starting material? to compare the acidity. The first product that we expect, the hydrogens connected, are actually more acidic than our starting material. Which means the instant I form the quote-unquote product, it reacts before our starting reactant reacted. Right? So we would have to be aware of that acid-base chemistry when we run the reaction. Okay? Or you memorize that when it's under basic conditions, you replace all the hydrogens with bromine. Okay? Those are your options. You now have experience with both. You can decide where your threshold is. Okay? Just realize that in a straight multiple choice, you'll probably see a bunch of different answers. In a short answer, I might explain why or ask, why did it continue? Why did it not stop at this? Okay? With the ability to also ask short answers, I will probe at you and be like, did you do more than just memorize? Can you pass the class by just memorization for the multiple choice?
Yes.
If you look at the division of points, you absolutely can, but you have to get every single multiple choice question right. Yes?
What can you end up getting, or do you have to worry about any of your secondary reactions, like the bromine reconstituting into, or the bromide and hydrogen reconstituting at all, or anything like refreshing? Do we have to worry about that?
So as far as reversibility, we don't have to worry about reversibility yet. You said hydride reconstituting.
No, sorry. That's probably,
We get H minus, we get Br minus. Byproduct of that first step is H2. Do I have to be concerned about H2 coming back on the reaction?
No.
Why not?
Because it's H2 is stable.
H2 is a gas. It bubbles out of the reaction. It's literally gone. That's why I don't have to worry about it. Okay? I could also reference the pKa difference. The pKa difference establishes that it's not reversible. Okay? Do I have to be concerned that the Br minus could go through and do something?
Like bromine, is there any way that you can like refresh your bromines with each other? Or do you have to
get the bromide to react with a bromine, well, bromine is Br2.
Yeah.
That's not going to do anything useful.
Yeah.
That's cyclic at best. Okay? For it to react off of your enolate, to pull a bromine off of that, well, now you've just reversed the reaction, which is exactly what I said, reversibility. Is there reversibility within this one? Not very much. Is reversibility a larger issue that you should be considering with each of your reactions? Yes. Okay. Is it one that's going to raise its head very violently yet? No. But is it there? Yes. And you do need to be cognizant that it could come up.
I guess what I was really trying to figure out is if you want to get it fully halogenated like that, are you going to have to do a 6-to-1 bromine to whatever your mixture is?
That's a more interesting question. If I wanted to actually obtain this product in a decent yield, do I have to more carefully weigh out the amount of substances I'm using? Absolutely. Because if I put this in as a 1-to-1 ratio, what happens? I will get trace amounts of this. Then I'll get trace amounts of with 2 bromines, with 1 bromine, with 4 bromines, with 5 bromines. I get the same issue that we had with that amine acting as a nucleophile. So yes, I have to be aware of that when I run the reaction.
Just like the amine, I'm going to have to flood it in order to push it.
Yep.
all the way. That's the only one that I can push to.
Yes, you can't push to any of the intermediates.
Okay.
Okay? So what if I do want to push to an intermediate? What if I just want 1 bromine on there? Could I possibly stop it?
Can you use one of the non-BR2?
No.
For that?
Yeah.
Yeah, I could stop it. How? Why does I change the conditions? Why does changing the conditions result in the formation of only the 1 product?
Because the product is not more acidic.
Okay. I like where you're going. You've got the right idea. Up here, we're talking about our expected product being more acidic than our starting material. Why were we concerned about our materials being acidic?
Because it was in basic conditions.
Am I concerned about it being acidic anymore? What am I concerned about it? Being basic. Okay? Because I'm under acidic conditions. The very first step under acidic conditions with our enol is to do what? Neutralize the acid. How? Keto-enol is multiple steps. I want a single step. How do I neutralize the acid?
You donate an electron from
I donate electrons from
oxygen to hydrogen.
that carbonyl compound from the oxygen to that hydrogen. Okay? So that compound, or let's assume we made our product, what do I need to evaluate to decide why it would stop? What am I now comparing between these two reactions?
Charge, size.
Not quite. We still have to know where to start our focus.
We have to figure out where the chemistry
Okay?
happened.
So Mustafa had the right idea. We were talking about the top one, our top reaction, which one was more acidic. Do I care about which one's more acidic? No, because what's happening in our first step? What's it acting as? It's acting as a base. Which of these materials, the expected one-step product versus our starting material, is more basic? Okay. This now becomes a little bit more challenging because it flips, and depending on how you memorized first semester ranking of acids, you may have shot yourself in the foot for ranking bases. If you've been paying attention to how we've been talking about addressing it, it's the exact same protocol. What does a base need to do? Okay. That base needs to donate electrons. Where are the electrons? Oxygen versus oxygen. Yeah? Okay. We start with charge. Oxygen versus oxygen. Is there a difference in charge? No. You'll notice I'm also pointing at the reactant. When we talked about ranking acids, did we look at the reactant? No. We looked at the conjugate base. Why would we look at the conjugate base?
Because we want to check the stability of the conjugate base.
But why couldn't I have checked the stability of the reactant? Because that's what I'm doing right now. In OChem, what do we do? Big metacognitive stuff. In OChem, we study carbon. How do we study carbon? The way that carbon reacts. How does carbon react?
By sharing electrons.
By sharing electrons. If I look at an acid, what is the role of an acid? To give away protons. What about that has anything to do with electrons?
No.
Nothing. So what do? When we look at ranking acids, we look at the stability of the conjugate base, because what do we see in the conjugate base?
Electrons.
Electrons. That's why we look at ranking stabilities of conjugate bases when we're looking at acid strengths. When I move to ranking bases, should I be looking at the conjugate acid? Well, again, our reasoning comes back to what are we studying? Electrons. What is the role of a base? Donating electrons, which means
We study the
they're already freaking there. I don't have to do anything else. I just look at that starting structure and I evaluate right out of the gate. I don't have to do any fancy footwork like I did for the acids. This is why it's so important to know those definitions and to apply them. So oxygen to oxygen, the charge is the same, so no difference. So we move to the next thing. Charge, then size. Oxygen versus oxygen. Same. Next. Electronegativity. Oxygen versus oxygen. Same. Resonance. Okay. There is some resonance, and you're welcome to do that with the pi bond. Is that resonance an effect that we should be concerned about? No, because it's the same, which means that we mean
Yes.
the next one,
Induction.
induction. Is there a difference in induction between these?
Yes.
Yes. Bromine versus hydrogen. Bromine is more electronegative than hydrogen, which means what is that bromine doing? Pulling the electrons, which means the electrons on this oxygen are going where? Towards the bromine, ultimately into the structure. What must a base do? Donate electrons where? Outside the structure. Once we add a single bromine on, those electrons are being pulled into the structure, the complete opposite direction they need to be to act as a base, which means the product after one substitution is less basic than we started, which means it won't react with the acid, stops after one substitution. Whoa! Okay. All of those processes that we just walked through are basics that you already know. Okay? And it's a question of applying that knowledge through. Okay? You don't have to apply it because you can just memorize it. Okay? You will find very quickly lots of memorization. Okay? So, what happens here? This is one that I would probably argue you should push towards memorization. Okay? Cardi talks about it in this chapter. I'm a bit upset with that because the mechanism behind it is not this chapter. It's actually Unit 3. Okay? So what happens? Basic conditions in BR2, what happens? We do substitute out all of those hydrogens, replace them with bromine. They're only on one side, so we don't have to worry about them going any other direction, right? So we only have that one side. That's not the product, right? What can you tell me about that bromine?
They're all electron withdrawing.
They are all electron withdrawing, which means that carbon is really partially positive. Why is that a problem? What are we next to?
Partially positive carbon.
Okay, a partially positive carbon. There's a lot of repulsion there. Okay? So I wonder if we could find something in solution that could potentially stabilize one of those positives. Mildly subtle.
Is it hydroxide?
What happens when that attacks? The pi bond is arguably the weakest bond. Okay? This runs into kind of some mechanistic fights, so don't stress about those. We'd have a negative oxygen. Negative oxygen is not happy, so what does it do? It needs to find some place positive. Is there some place positive nearby? Yeah, like what? The carbon that was literally there. So what happens? The electrons come back down. But we've now exceeded the octet on the carbon. What leaving group? Is carbon a good leaving group?
Yeah.
No, the CBR group might be.
So you
Okay.
provide the stabilizer the carbon.
It is all of those bromines being electronegative enough to stabilize the negative carbon. That's what allows that to leave. Okay? Negative carbon, is that stable? No, so what does it want?
Another bromine?
It's acting as a nucleophile.
Okay, we could try and do another bromine. That's not a bad idea because there's BR2 floating around. It turns out there's actually something that is more reactive closer to it. So instead of going with bromine, I know where you're aiming at. Why were you suggesting bromine? What is it bromine supplying to react with this?
It's a positive and negative.
Positive, yeah. We want a positive to react with that. Is there a positive nearby?
Sodium is a solid.
No, it's
Or it goes out.
H plus, yeah.
What functional group is that?
Carboxylic.
That's a carboxylic acid. What happens? An acid-base reaction. to form C or HCBr3 and then the conjugate base. What is step 2? Put the hydrogen back on. There's our final product. Okay? This is a tricky one because if we go through and look at the mechanism, we might say, well, there it is, I'm done. No, you're not. You've created a reactive species that reacts internally, that gets rid of the product. You then have to add acid to fix it. Okay? So there are multiple reactions, particularly making alkynes, terminal alkynes, where you add a bunch of base, but then it says to add you have to add 3 equivalents of base as opposed to 2 equivalents. You're like, well, don't I have to just do 2 eliminations? You end up forming a structure that reacts with the base, not in a way you wanted it to. Okay, so we have to counteract that. Okay, the same thing is happening here. We would remove that. If we were asked to draw the mechanism, we would have to show what's in green. We could then say we add H plus to get the last step. So that last sequence in green, a lot of people don't like showing. You have to show it if it's a mechanism. If it's a mechanism. What if you're just asked to predict the product? What do you got to show? You just draw the product and you're done. Okay. This is a favorite question for the ACS. Okay, I've seen it pop up a couple times. Which compound will give the yellow solid HCl3 when mixed with iodine and sodium hydroxide? Why does that have anything to do with this? Iodine and sodium hydroxide.
Replace that with I2. And then
Instead of that being Br2, make it I2. Right? Instead of it being HCBr3, it would be HCI3. Right? For this reaction to work, I had to have that carbon with 3 halogens connected to it. How did I get the halogens on there? What did they replace? Hydrogens, which means I had to have a methyl next to a ketone to allow that to happen. So if we looked at the structures, usually you see something, I'm sure I'll butcher it. You could see something like that. Of course, I draw the correct answer right out of the gate. That's, well, sure, why not? And I'm out of space, conveniently. Okay? And you just see a bunch of these structures, and almost guaranteed, sorry, I gotta throw one more in. You'd see all these structures and be like, what do those have to do with those reagents? You would have to recognize the pattern behind here. It's cool it happens. Okay? And what are we looking for? We need that CH3 next to a carbonyl. First one has it. The second one is all sorts of effed up. Why? Octet around our carbon. It did have the methyl next to it, but if your structure is invalid, that doesn't count. The next one, you have the phenyl ring. The position right next to it doesn't have hydrogen. That one doesn't have hydrogen. Last one, it's a carboxylic acid. It's trying to trigger that officially. We should throw that on. Okay. What they're trying to do is be like, you're going to recognize the pattern and say, because that was a product in that reaction, I'm going to say that's the answer. So they're playing a structure memorization game with you. How good were you at memorizing? Okay. Then you won't get that one wrong. Okay? Make sense? Why is this such a big test question? They usually throw it in with another word. They usually call it the iodoform. Okay, the iodoform test. Okay, some people use it, like I think Mesa does a lab with it in 152. Okay, the reaction itself happens insanely fast. So if I have an unknown compound, I add some iodine and sodium hydroxide. If I see this precipitate right away, what do I know about my unknown compound?
You have a methyl ketone. I
have a methyl ketone. It allows me to classify the reaction or the structure, some aspect of the structure very, very, very quickly. Okay, a matter of minutes. Okay, we talked about this with the Lucas test, same idea. Okay? Those reactions, because they're so commonly used in classification, get named reactions. This one's called the haloform or the iodoform. Haloform is general. Iodoform is very specific to the yellow solid. Why did we get a yellow solid? Why would we expect this to precipitate out? It's very large, relatively nonpolar. We're in a water environment. Okay? So it doesn't dissolve in the water. I believe bromoform and the chloroform is just clear, so you might see two layers form. I don't know about the bromoform. Okay? But the iodoform actually forms a solid. Okay? Okay, choice of base. We actually talked about this one already. What's the difference between these? So we should be able to do this pretty fast. What's our difference? The reagent, it's the base used. Okay? We're looking at ethoxide versus hydride versus amide. So which atom is holding the negative charge? Which of those is the strongest base? Hydride, how do we evaluate that? Charge, they're all negatively charged. Size. Hydrogen's the smallest. Smaller can't stabilize the negative charge, which means most reactive. So hydride is by far the strongest base. We could go through, let's see if I've got them here. We could go through and look up the pKa's for these compounds. Okay? If we evaluate, we look at the conjugate acids for the bases to figure out their pKa's. Ethanol has a pK of about 16. The amide has a pK of 36, which means its conjugate base is a very strong base. Okay? That's where we can do the conjugates as relationships. We had that conversation earlier that Mustafa thankfully brought up for us. Okay? Hydride, you'll notice we don't have a conjugate acid. Why not? It's a gas that just bubbles out of solution. So we can say, we don't need to worry about its pKa because it just disappeared. It's kind of a cop-out. Okay, we could look at its pKa. How stable is H-?
No.
So unstable. What happens to its pKa? 60, 70, 80. Okay. Really, 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 really large pKa's. And large pKa's are weaker acids. Okay. So we could quantify those differences. Or we could use our charge balances. You remember when we quantified things in 152, we had to run a bunch of calculations, right? How many calculations have I asked you to run? You're like, none. Actually, I have asked you to run calculations. Charge, size, electronegativity, resonance, induction. Those 5 rules are explained as a result of the calculations. Without the calculations, we don't get those rules. So the calculations are the underpinnings of those rules. Okay? That's why they work. The evidence supports them. Okay? We talked briefly about the nucleophilicity, right? Which one of those is the strongest nucleophile?
The nitrogen thing.
Okay, so to be a nucleophile, what do we need to do? Donate electrons. To be a base, what do you have to do? Donate electrons. Rob started to go off on it, actually. Sorry, I interrupted you. What was the nucleophile?
Donate electrons other than hydrogen.
To something other than hydrogen. Where are atoms other than hydrogen?
Inside the structure.
Inside the structure. So to act as a nucleophile, we need to be
Big, bulky.
because to get inside the structure, we want the biggest thing possible because it's totally just going to avoid all those other things. We want the smallest thing possible to avoid interacting with those hydrogens. The bigger it is, the more likely it interacts with the hydrogens and it acts as a base instead of a nucleophile. So our nucleophiles need to be small. So which of those is the smallest? Hydride is the biggest. You're like, Mark, it's small. It's just you said it was the smallest atom. Yes, it is. It is the smallest atom. It is also so incredibly unstable that the hydride ion does not dissolve, which means it stays a solid. The only place it can interact is on the surface of a solid, not all the way around the atom. So the effective size of hydride is massive, which is why it acts exclusively as a base. It cannot act as a nucleophile. Right? The ethoxide is the next best bet because the amide has the steric hindrance of those propyls. So the ethoxide would be our best nucleophile here. Okay? Sodium hydride is so reactive we tend to avoid using it. Okay? So in favor of typically going to the negative nitrogen if I wanted a strong base. Okay? This base gets so commonly used that it is sometimes abbreviated. It is abbreviated LDA because isopropylamine totally has all those letters. Oh wait, it did. LDA is lithium diisopropylamine. Okay? So sometimes you'll see reference to LDA, it's referring to that structure. How much of as your instructor in your experience so far, how much do I press you to memorize things? No, I want you to look at structures. So which do you expect to see on your test, LDA or the structure? The structure. Are you responsible for LDA? Yes. Okay. When it comes to my tests, I'll give you both because I'm trying to reinforce that structural information but also get the name in there. Why? Because I don't write the final. Okay. So I want you to have some of that exposure to be able to pull up some of those reagent names. Okay. I already addressed that. Enolate chemistry. Okay. Which one of these is more acidic? Left or right? Left. Good answer. That was fast. Why? More resonance. Okay? So we can go through the same rules. Notice we said more acidic. Okay? We got an answer right away. To rank acidity, typically we'd have to draw out our conjugate bases so that we could see the electrons. Why were you able to do that without drawing it out, Milana? Okay, so one option is she jumped to, there's two, so we're saying an inductive effect. Okay, that gets to the answer of it being more acidic, but if I ask you to explain why, you're going to be dead in the water, right? I won't give you points because it's not an inductive effect. That's still an inductive effect. Okay. Ideally, what happens is that you've done this enough that what happens? What I just drew shows up where? In your head. And you immediately see those structures in your head. And you immediately are able to draw out those resonance in your head to see that one had more resonance than the other. That's the practice of OChem. Okay? Sometimes, if it's like this, where you could pull induction, sometimes that works. It doesn't always. So I just want you to be aware of that limitation behind that process. Okay? Make sense? Which base should I use to deprotonate these? Does it matter?
Yes.
It will matter. And the only reason it matters is because we care about our personal safety and theoretically the safety of everybody else in the world. Okay? Green chemistry. We want to use the weakest base that does what it needs to. Because if I use an excessively strong base, I end up risking my life and potentially everybody else's life. Okay? If we said this one was more acidic, which base should I use? The weakest base possible. If this one's less acidic, I need to use a stronger base. What else would I have to evaluate within this? reversibility of the arrows. Okay? Because if it's a reversible reaction, what does that mean about the strength of the base I used? It's even weaker because it's a reversible reaction. If it is not reversible, I'm going to try and push a stronger base because I don't want it to reverse. Okay? Those are considerations to keep in mind when we look at our reagents. Okay? Which gets us to our unsymmetrical ketones. Everything we've seen so far was symmetric. When we go through and look at this starting material, I'm going to get away with just showing the red and the blue hydrogen. Okay? Officially, there's another red hydrogen, but it's the same, so we don't worry about it. Which hydrogen do I pull off?
The red hydrogen.
Okay. So the theory is to pull off the red hydrogen. If I use that reagent, also known as T-butoxide, pulls off the blue hydrogen. So you're wrong. Say that again? So we could start referencing tertiary cations. That becomes a little bit dangerous because we look at our intermediate. I have an anion. Tertiary anions are less stable. So I like where you're starting to go. You're evaluating the stability of our intermediates. But if I look at these two, officially I shouldn't have that hydrogen on there. Should I be looking at the intermediates to predict their reactivity? You're like, sure, of course. What is the relationship between the intermediate and what I'm showing as the final product here? Say it again.
Resonance.
These are resonance. Which of these two resonance structures should I be using to evaluate my argument? Middle or right?
Right.
The right, because
The charge is on the oxygen.
the charge is on the oxygen. When I evaluate those two structures, the reactivity difference is centered on the pi bond. The bottom one, the pi bond, is more substituted than the top. That makes the bottom one more stable, which makes it a thermodynamic enolate. The top one becomes a kinetic enolate. The base that I used here was a sterically hindered, or not sterically hindered, but a weak base. Okay? Because it's a weak base, I'm going to form the most stable product I can possibly form. So I get the thermodynamic enolate. What happens if I switch it up and say use sodium hydride now? Now I pull off the red one. The hydride is now so reactive as a structure that it's going to react with the most accessible hydrogen first, the red one, but that reaction is irreversible. So I get stuck at the kinetic product. Okay? This is a heavy determination between kinetic and thermodynamic. We looked at it with temperatures. Hot reactions favored thermodynamic. Cold reactions favored kinetic. Those were reagent conditions. We are changing the choice of base. Is that also a reagent condition? Yes. So we can use temperature and we can use the strength of our base to dictate which product we get, be it kinetic or thermodynamic. All of that can be used through an energy diagram, okay, which I will leave you to go through and do on your own, and if you would like to confirm it with me, you can. Okay? I would recommend you do that, okay, because you've already seen my fondness of energy diagrams. Okay? But we are a bit short on time. What we see here looks like a giant freaking mess, but if we look at the very center, we're starting with a keto, and what can the ketone do? It can become an enolate using bases, or it can become an enol using acid. What can happen when I take my keto form? Well, if I add a strong base in Rx, what do? Substitution reaction, okay? Which we already talked about. So what this slide has on it is something that would classically fit in a different textbook. It doesn't fit in Carty's textbook because this one shows all of the reactions of the ketone functional group. We haven't talked about all of these. By the end of Unit 3, we will have. Okay? So I just want you to be aware of that. Chapter 7 We're taking polar pi bonds. Okay. Did we just address polar pi bonds? Yeah, you're shaking your head. Yeah, we did, didn't we? We looked at that carbonyl. Were we looking at the polar pi bond as the reactivity? No, we were actually evaluating the acidity next door. Now what we're going to go through and do when we move into chapter 17 and 18 is say that we have an electrophile in this structure, that carbon becomes electrophilic. So now I want to add all of these nucleophiles that we've talked about for now 6 months, like 6 months, Chem 1, okay, and react them with that carbon. What's going to happen? Chapter 17 takes all of the really stupidly strong nucleophiles. So negatively charged things like hydrogen. Can't have a negative hydrogen? Yes, you can. You just can't be sodium hydride, not a nucleophile. Okay? Negative carbons. That's it. That's ultimately chapter 17. Negative carbons, negative hydrogens. What's chapter 18? Negative oxygens, negative nitrogens. What's the difference between carbon and hydrogen versus nitrogen and oxygen? Electronegativity. What is that going to do to our nucleophilicity?
It's going to decrease it.
Yes. Chapter 17 is a little bit easier because these are typically not equilibrium reactions because we're using stupidly strong nucleophiles, hydrogen and carbon. When we move into chapter 18, they become weaker nucleophiles, which means we get lots of equilibria. Okay? With that, I have to stop.